So moving on. So we're going to get into now doing some calculations, okay? Sorry, my phone keeps turning off, and I want to make sure that I'm not talking too long, okay? So matter can absorb or emit any quantity of energy, but only in quantized amounts. So this is the basis of the theory of quantum mechanics, okay? Or what you'll often hear me say, QM, or quantum theory, okay? So two very famous gentlemen, Max Planck and Albert Einstein, came up with this idea, okay? And also came up with this famous equation, E photon. So what that refers to is the energy of one single photon. What is a photon? Well, a photon is a packet of light. So you could think of it as a particle, okay? Or a packet of light, a packet of energy, one singular photon, okay? And this equation says the energy of that photon is h, which as it turns out, h equals Planck's constant, Max Planck's constant. And it has a crazy value of 6.626 times 10 to the minus 34 joules times seconds, okay, is our units for h. Let me make this h a little bit more clear. Okay, h. So this equation says the energy of a singular photon can be just Planck's constant times its frequency. And if you think about that for a second, Planck's constant is a joule times a second, okay, for h. And then nu, frequency, is 1 over seconds. So that gives us just units of joules, which is a unit of energy. So great. Or because we know that frequency, right, we know lambda, or excuse me, nu times lambda equals the speed of light, then this equation can also be written as h times c, speed of light, divided by lambda, okay? And if we think about the units there, we know h is a joule times a second. We know speed of light, c, is meters per second. And we know lambda has units of meters, so that's c and that's lambda. So now if we look at all of this here, the second and the second cancel, the meter and the meter cancel, and then once again I'm left with energy units, joules, okay? And then I'll also remind you, because we're going to use nanometers quite a bit in this class, because the visible spectrum is in nanometers. So I'm going to remind you here, we want to be really good at converting with nanometers. So we can say 1 meter equals 1 times 10 to the minus 9 nanometers. Or I can say 1 times 10 to the minus 9 meters equals 1 nanometer. So either of those will work for us, but we want to be able to comfortably interconvert those units, okay? So let's do a couple calculations. So number one, calculate the energy of one blue photon, all right? So let's do that. So number one, so that's going to be E photon equals, and we can either use h times nu, so let's say h times nu, or we can use h times c divided by lambda. And you notice here, I just told you one blue photon. I didn't tell you the actual wavelength. But if I go back now and look at my electromagnetic spectrum, we'll say blue. I could pick 450 if I want. I'm just going to say 400 to make the calculation easier. So this is just approximate, this example. So we'll just say assume lambda equals 400 point nanometers, all right? So here's how we do this calculation now. So because I have lambda, I'm going to choose the h times c divided by wavelength, okay? And I also know that I have to get this nanometers into meters to use this equation. So I'm going to say in 1 nanometer, there's 1 times 10 to the minus 9 meters, okay? And very quickly, I'm pretty good at doing this, but I understand if you need more practice. This is going to be 4.00 times 10 to the minus 7 meters. Okay? So all I did was, because this is 4 times 10 to the positive 2, and this is 1 times 10 to the minus 9, I just subtracted the exponents. All right? So now I can say E photon equals 6.626 times 10 minus 34 joules times seconds times C, which is 2.998 times 10 to the 8 meters per second. You don't have to memorize these constants. I will give them to you. And that's divided by 4.0 times 10 to the minus 7 meters. So this is kind of like thermo, where this is just largely plug and chug, but we've got to get, we've got to make sure we're putting things into our calculator correctly. Okay, so I've got 6.626 times 10 minus 34, and I'm going to say times 2.998 e to the 8 equals, and then now I'm going to say divided by 4e minus 7 equals, and that's right, because I got my cheater notes right here telling me what the answer is. Okay, we'll say with 3 sig figs, because I had 3 sig figs in the wavelength, 4.97 times 10 to the minus 19 joules. That's the answer for number 1. Okay. Calculate the energy of 1 mole of blue photons. So all I have to do now is just say this number, and look, I'll do it with the stoichiometry so you can see what I'm doing. So that's joule per single 1 photon. And so now I'm just going to multiply it by 6.022 times 10 to the 23 photons in 1 mole. And so now I can say times 6.022 E23 equals, yep, and that looks right. So that gives me 2.99 times 10 to the 5 joules. And very quickly I can see that that is the same as that's joules per mole, because I said per mole of photon. That's 299 kilojoules per mole. Okay? And then now, finally, this third one is going to be a little bit more tricky, but you'll actually see it's not so bad once I get it set up. Calculate the number of photons per second in a 60-watt blue light bulb. Let's talk about the watt, okay? So you're probably all familiar with watts, right? Because you've looked at a light bulb before. Maybe hopefully not stared at the light bulb, but you've looked at the power rating on the light bulb. So a watt, 1 watt is symbol W, and that equals 1 joule per second. So 60 watts is 60 joules per second, okay? So, so actually let's write that down, because maybe this might be confusing later on. So 60 watts is 60 joules per second, because 1 watt equals 1 joule per second. Okay, great. So now how do we do this? So I'll remind you that that number we calculated from E photon is 4.97 times 10 to the minus 19 joules per 1 photon. Okay? And so what we're trying to do is calculate the number of photons per second. So I wrote this upside down, right? So what I want to do is really know the number of photons in this thing. So I'm going to start with this number, just like we do with our stoichiometry. I read this problem, 60 watts is the number in this problem. That's the number I'm going to start with, okay? And so I'm going to say that's 60 joules in 1 second. So you can see now, this is why I wrote this down backwards initially, because now what I recognize is I need to convert joules into number of photons, and that's what that number tells me. That number tells me 4.97 times 10 to the minus 19 joules is 1 photon, okay? And so now the problem is asking me to calculate the number of photons per second in 1 blue light bulb, And this is literally all I have to do is just divide the power, this is a unit of power, the watts by the energy, okay? Joule and joules cancels. And so now, let's see, I get 60 divided by 4.97 E19 minus equals, and yes, that is correct. So we'll say because 60 watt, technically that's only 1 sig fig. Let's cheat and put a decimal there to make it 2 sig figs. Okay, so that would be 1.2 times 10 to the 20 photons every second. So think about that. When you have a 60 watt light bulb, every second you're getting 1.2 times 10 to the 20 photons, little packets of energy coming out of there. So that's a ton of energy being emitted, okay? So there's one more, let's see here. Do I want to pick up this concept? Actually, I think I'll wait. I'll do this section 7.3 on the next slide. I've been doing about 30 minutes. That's a pretty good length of a video for this section. Okay, folks, I'll see you in the next video.